So we're doing space complexity, and just to recall from previous definitions, remember a space-bounded Turing machine, what we have is we have a read-only input, and then we have a workspace or work table. Oh, sorry, I haven't shared my screen yet. All right, is everything visible? Can you see and hear me?
Yeah.
Yeah. Okay.
This would be the reminder to also start recording.
Yes, the recording has started. Yes. Okay, so in a space-bounded Turing machine, the input is read-only, and there's a workspace, a work tape, which is read-write. And so the space-bound is really on the workspace tape. So PSPACE is essentially polynomial space algorithms. So for PSPACE, you don't necessarily need the separate work tape. Like you can just work with the input tape. So this is just a standard polynomial space algorithm. But the nice thing about having a read-only input tape is the space could actually be less than n. And so we can define this class called L, which is log space, and NL, which is non-deterministic log space. So essentially, they only have enough space to store the index of where the head is. Does that make sense? So the head index can be stored, but that's it. That's all that they have. And if you think about it, why is it log space? Why don't we go below that? So at least from the perspectives of this class, we're looking at deciding languages exactly. In less than log n space, you cannot even store the length of you can't even write down the input length. Of course, there are certain languages that you can decide in even less than log space, and you could look at things like finite automata or very simple, languages of that form. But in general, log space is really where things get interesting, because at least from a Turing machine and computability perspective, because this is you can at least write down the input length. All right. So any questions about the definition of the space classes? Right.
Going back to what you're talking about, log spaces. What about streaming algorithms that use very little space? Does it count the total space they've used as a lot, or the fact that?
So that's a different model of computation. In streaming algorithms, typically you think of the input is read only, and it's read only in one direction. The head can only move to the right.
I see.
And also in streaming algorithms, not all of them, but for many of them, one gets an approximate answer. So it isn't used to decide languages exactly, although there are some of them that are exact, but still, when you think of sublinear space algorithms, they're approximate algorithms. And so far in the course, everything we're talking about is exact algorithms. So to bring in a notion of streaming, or like less than log n space, or like things like that, one has to bring in randomization, which would require a lot of development formally. Okay, so a very important, and as we'll see over the next few weeks, that we actually know a fair bit about space complexity and the way it relates to non-determinism and complementation in a way that we don't know about time. So we have some very interesting theorems that we'll be seeing. One of the most important concepts for understanding space complexity is the notion of a configuration graph. Okay, so what is a configuration graph? So given a Turing machine M, and we'll think of space-bounded Turing machine M, and input X, we define the configuration graph, GMX. Okay, so I'm going to define what this graph is. So recall that the state, the total state, right? This is not just this the head, the state of the finite machine, but in some sense the total state of M can be represented as a string. Like you represent it as a string with the tape contents and the sort of the state machine state. Sorry, this is poorly worded on my part. I mean, what I mean by total state here is different from this state. This is the state of the machine, sort of, the finite state machine part, state machine state, and so you can represent it as a string with the tape contents and the state machine state at the head position. So we discussed this earlier during the proof of the Cook-Levin theorem, where you can write things out as sigma 1, sigma 2, sigma 3, up to some q, sigma I. So this is sort of saying that the head is actually pointing to qi, sigma I plus 1, to sigma whatever space bound there is. Right, so any questions about this? So we can represent the entire state as a string. Okay. So in GMX, V is the set of all such strings of length at most s times n. So what is s times n? So it's a space-bounded machine. N is the length of x. So if it's a space-bounded machine, then the vertex set is just the set of all possible configurations. This is the set of all possible configurations. It's important to note that the set of possible configurations is finite because the space is bounded. Right? So the space is bounded. Okay? Now, E, the edges, is going to be, there's an edge UV, okay, and this is a directed edge. So E is a directed set. This is directed. If M can move from the configuration U to the configuration V. Okay, does this make sense? So the configuration graph basically says these are all the transitions, but the transition, not of the transition function, the transition of the entire machine goes from one configuration to the next, and you draw a graph that just represents all of this information. Okay. And then we define the start configuration. The start configuration, this is basically the initial configuration of M on input X, right? So this clearly depends on X. And then we'll say there's something called the accepting configuration. So this is just a configuration with the accept state. So, without loss of generality, assume that the Turing machine clears out the tape on acceptance. So there is a unique accepting configuration. So I will refer to this as C start. That's the vertex, the starting configuration. and I will refer to this as C except. So I'll use C to denote configuration, and this also denotes a vertex, right? The starting configuration and the final configuration. Okay, any questions about what the configuration graph is? Again, it's a graph where vertices are configurations, edges represent a move from one configuration to the next. There's a starting configuration and there's an accepting configuration. Okay, so now let me give you a very useful claim that we will use. So I'll say M accepts X if and only if what in the configuration graph? What can you say about the configuration graph if M accepts X? Any thoughts? So what does a path mean in the configuration graph?
Well, it's a series of transitions.
It's a series of transitions. So what it means is that the Turing machine can go from one configuration to another if there is a directed path from one to the other, right? Based on what you just said.
Yes.
So what does it mean? Okay, so let's step back. What does it mean for the Turing machine to accept an input? What configuration does it start from and what configuration does it have to get to?
Well, it has to start in the starting configuration,
Right.
and has to end in the ending configuration, right?
In the accepting
Ending state.
configuration.
Yes, that's what I meant.
And so this is an if and only if, right? So if your Turing machine can go from the start configuration to the accepting configuration using a series of moves, right? Regardless of this includes non-determinism. I'm not saying M is deterministic because I said if M can move. So if it can get from the start configuration to the accepting configuration, that means it must accept the string. So let me write out a claim here. If and only if GMX has a directed path from C start to C accept. So is this claim clear? Do you see why it's true? Questions? Okay. All right. Now let me ask you a question. For an S of n space Turing machine M. By the way, it could be non-deterministic. G of mx has, how many vertices does it have? Does it have poly Sn vertices? Does it have O of 2 to the Sn vertices? Or is it 2 to the O of Sn? Give me the best answer. Okay, and let me just run the poll. There it is. All right. How many vertices does the configuration graph have? How many vertices does the configuration graph have? So the answer is 2 to the O of Sn. Why? Because a configuration is a string of length Sn over the alphabet sigma union q. Right? So even if sigma was binary, the number of states is potentially larger, and so it's a string where the alphabet is constant size. So therefore, the number of configurations, like the right bound, the number of total configurations is the sum of this quantity to the power Sn, which is 2 to the O of Sn. It's not O of 2 to the Sn, it's 2 to the O of Sn. Okay? I'll write a simple claim over here. I'll say G of mx has out degree 1 if and only if m is deterministic. And technically deterministic on x, but we can say deterministic, right? So what's nice here is that we're able to represent non-determinism and determinism just through the configuration graph, and it's all about out degree, because if the out degree is 1, then it's deterministic. From any configuration, there's only one configuration to move to. If it's non-deterministic, there are multiple choices, which is represented in the out degree. So this bound is going to be very important for us. And I'm now going to prove a short but very useful theorem that will tell us how to relate space and time. So I'm going to club everything together. So I'll say d time of S of n is a subset of space S of n, which is a subset of non-deterministic space S of n, which is a subset of d time 2 to the O of S of n. Okay, so these are sort of, this is trivial. This is easy. This is trivial. This is the interesting one. What it says is that space Sn is contained in d time of exponent, like by exponentiating. So 2 to the O of Sn. So what is the proof? So consider L in n space S of n. Consider L in n space S of n. And again, we always assume that S of n is at least log n, and think of S of n to be a well-behaved function, some polynomial function. Technically, it's something that is time and space constructible. So consider L that is in n space of S of n. There is an NTM M using S of n space, or I should say technically O of S of n space, deciding L. So now I'm going to describe a Turing machine that runs in deterministic time of 2 to the O of S of n that decides this language. So design M prime that So what it's going to do is that constructs the graph of the configuration graph of M on input X. So what does it have to do? List out the vertices, right? And this can be done in 2 to the O of S of n time. List out the edges. List out edges. Again, this can be done in 2 to the O of S of n. It simply has to go and check for every configuration what are the neighboring configurations, right? So it can construct the adjacency list, find C start. That's again 2 to the O of S of n time C start and C accept. And then basically it runs DFS from C start to get path to C accept, if it exists, right? So it just runs DFS. Sorry, let me show you that entire argument. And I'm just going to put the fifth part over here because I don't want to, because I think the argument is basically done. It runs DFS from C start to get it C accept, and no, accept if and only if a path exists. Again, the DFS runs in the same amount of time. It's just linear in the number of vertices. Okay, so that completes the proof. Okay, so is that clear? You have non-deterministic space of S of n lies in deterministic space of 2 to the O of S of n. This is a very important bound. So any questions about this, please ask me. Is the proof clear?
So the reason why it's not infinite is because it has a S of n space, right?
It's bounded. The space is bounded. So you've been told that this machine only uses this much space.
Right. Okay.
So therefore, in some sense, the halting problem is decidable now for such a machine.
Of course, right. But if we had not bounded it, had not space bounded it, then if we were to construct a configuration graph, then it would be infinite.
Exactly, right? So you have to know, which is why, okay, so in my definition of a configuration graph, I said given a space-bounded Turing machine.
I see.
You have to have a space, and you need to know what the space bound is. So you're given a machine, you're given the space bound and an input, and then you basically construct the configuration graph.
Gotcha.
Any questions? Okay. Is this clear? Because we're going to sort of build on this and go forward. It's a good time to ask questions.
This is basically like it's like basically a brute force kind of thing to solve the halting problem. I guess with this small small set of, or rather finite set of states.
Exactly. Well, when it's a finite set of states, it just becomes a graph reachability problem.
Yeah.
But I think this connection of space-bounded Turing machines to the configuration graph is something that is going to be a thread for the next few weeks when we understand space-bounded computation.
Isn't it possible that in your configuration graph that it could just never reach an accepting state it could just keep looping around and around, even if it's finite.
Sure. I mean, you could have something that loops around, but the point is, that's just a graph problem that you can decide. Like, you can find loops using BFS.
I see that.
Right. So the thing is, by doing a DFS, you can basically determine, or BFS or DFS, any sort of graph walking procedure. You can find if there is a path, even if there are loops.
Right.
I mean, the DFS isn't as, sort of stupid as just walking through each configuration without keeping track, right? It's going to keep track of everything and build the DFS forest.
Sure.
Maybe another way to think of it is, if you did BFS, you'd get like you could get like a shortest path.
Gotcha.
Okay. Any questions? Okay, and then finally, I want to give you another statement. Well, not finally, but I want to give you another statement, relating all these classes that we've seen so far. So, and this is relatively, again, simple claim here is that NP is in PSPACE, right? And this is simply, try all certificates. Try all certificates, reuse the space. And so similarly, co-NP is also in PSPACE. Indeed, if you think about it, PSPACE is really powerful. And we'll see that it's going to be much more powerful, or seemingly much more powerful. We never know about these things, but maybe P is equal to NP, but seemingly it's much more powerful, right? Because you can do both NP and co-NP. Because you can just try out all the certificates and determine if a certificate exists or doesn't exist. So is this clear? Why NP is in PSPACE, or why co-NP is in PSPACE? Okay. Now that we have all of this, we have our previous bounds, let's try to relate all the classes that we have seen so far. So we have log space is in non-deterministic log space. This is just like saying that, it's also going to be contained in co of non-deterministic log space, this co-classes. Now, by this theorem that non-deterministic space is contained in exponentiating, and so the same is true for co-non-deterministic space, right? So whether L is in n space or co-n space, it doesn't matter, because as was suggested, it's like a brute force algorithm. It basically lists out all possible configurations and checks whether there is a path. Both of these lie in P. Now P lies in NP, and NP lies in PSPACE. And PSPACE lies in exponential time. And the reason that it lies in exponential time is, again, this statement here. But seemingly I forgot something, so let me say PSPACE. So PSPACE lies in NP space. And it also lies in co-NP space, which lies in exponential time. So maybe I'll draw this out as a figure so that you see it more clearly. Sitting sort of at the bottom of the hierarchy is log space. Log space is like this, pretty much in this setting is the simplest class we're looking at. So we have non-deterministic log space, and we have what's called co-non-deterministic log space. All of this lies in P. right? Now P lies in NP and co-NP. So here is NP, here is co-NP. Now this lies in P space. Now P space lies in NP space. And then there's co-NP space and all of that, and I'll explain, And that lies in exponential time. Okay, this is the picture, right? So L, you have NL and co-NL, which lies in P. So these are all subclasses of polynomial time. Log space and non-deterministic log space. Now this gives you NP and co-NP, which lie in P space, which lies in NP space, which lies in exponential time. Picture clear? Now what do we know? We know that P is not equal to exp. Remember, this was the time hierarchy theorem. There's also something called the space hierarchy theorem, which pretty much has the same proof. The space hierarchy theorem, and that says that L is not equal to P space. So what you have is P is not equal to exp, and L is not equal to P space. So what this says is if you're comparing time complexity classes amongst themselves and space complexity classes amongst themselves, then you have the separation. So L is not P space, but that's a huge, L to P space is huge. So what we actually know is that either L is not equal to P, or P is not equal to NP, or NP is not equal to P space. But any of these would be amazing things to prove. Remember, L means it's log space. So if you're saying L is equal to P, then you're saying all efficient algorithms that we have can actually be simulated with just logarithmic space. It seems like impossible. So any questions about this picture?
So L is not equal to P is another option for something that we can prove as a that would that also decide P is equal to NP or not?
No, probably not. But L equals to P is again like a big open problem, and that seems like it should just not be true. Like something says there's no way you can simulate things with just logarithmic space. Like imagine if you could basically say any efficient algorithm, the only extra space that you need is logarithmic in the input. But we don't know how to prove that. We don't even know if P is not equal to P space. It seems like P space, polynomial space, should be more powerful than polynomial time. But we don't know if that's the case.
Frustrating.
But for space complexity by itself, there are actually a bunch of surprising things that we do know. And I'll show you how the picture is going to simplify. So you say P space and NP space. Remarkably, we know that these are equal. P space is NP space, so non-determinism actually doesn't buy you anything in P space. These are actually the same. And another big surprise is that like you have NP and co-NP being different things, but NL and co-NL are actually also the same. So NP space is also equal to co-NP space because P space NP space is P space. So non-determinism doesn't actually buy you anything with space. Complementation also doesn't seem to buy you anything in space. These are both non-trivial theorems. And we're going to be proving both of these theorems. This theorem we'll do today. NL equal to co-NL we'll probably do in the next lecture or the next couple of lectures. Or we'll eventually get there. So is this clear? I mean, actually, and NL and co-NL, these might seem like really strange classes, and when we talk about them, they'll start making more sense. But P space you can understand, which is polynomial space. And non-deterministic polynomial space seemingly has no power, no extra power, meaning that at least in terms of these complexity classes, they're actually the same. So the picture that we have is actually these two are the same. These two are actually the same. and PSPACE and NPSPACE are the same. Any questions? So let's start with why PSPACE is equal to NPSPACE. And this is known as Savitch's theorem. And this is it's an old theorem from 1970. It says n space S of n is contained in deterministic space of S of n squared. So it says that non-deterministic space can be simulated with deterministic space with just a quadratic blow-up. And hence the union of C greater than 1 of n space n to the C is a subset of space. Technically it's, so you can think of it as n to the 2C, but this is the same thing. As that, right? So this is NP space, this side is P space. So Savitch's theorem says that non-deterministic space can be simulated with deterministic space with a quadratic blow-up in the space. So imagine, just to get you a sense of what this means, this is saying, like, suppose if you said non-deterministic time could be simulated with deterministic time with a quadratic blow-up. That would be amazing. Because it says that, for SAT formulas, if you can basically do them in non-deterministic linear time for like some special setting, then you could do it in deterministic quadratic time, which would be amazing. But, we don't think that is true. But Savitch shows that, sort of counterintuitively for space, actually, one does have this. So space behaves very different from time. Okay, any questions about the statement? Okay. So now let's do the proof. Proof is actually not that difficult once you have the right language about configuration graphs. So let's consider some language L in non-deterministic space of S of n. Okay, some language. So this means that there is a S of n space non-deterministic Turing machine M deciding L. And we need to construct another deterministic space machine that decides L. So now I'm going to tell you about how to do the description. So given input X, consider the graph that I'll say GMX. I'm saying consider it. We cannot construct it because constructing it would require too much space, right? We can't store all possible configurations, right? If we wanted to construct it explicitly, we would actually need 2 to the O of n space, right? We would need 2 to the O of n. We would need lots of space. So I just want you to consider it. And I'm going to show you sort of a thought process on how we're going to actually construct a deterministic space algorithm for this problem. So remember we said that we need to check if C start has a path to C except. And so we can imagine writing down these configurations. You can write down what C start is, you can write down what C except is. Now G has 2 to the O of Sn vertices. We cannot afford to write or construct G completely.
And because of that, we wouldn't be able to just automatically use BFS to solve
Exactly.
it.
We just can't use BFS on this. So Savitch gave a clever recursive idea. So Savitch said, okay, so let's define a procedure reach C, C prime, and I that outputs true if there exists a path from C to C prime of length at most 2 to the I, and sort of false otherwise. So this is just a Boolean procedure that's going to say true or false. Can you reach C prime from C? Can you go from C to C prime in 2 to the I steps in this graph? Okay? And so what we know is that, so remember we said that G has 2 to the O of S of n vertices. So reach C start, C except. So for the O, I'll just put some explicit constant there. C times S of n is true if and only if X is in the language. Right? This is just saying that if there exists a path, the path has length at most the number of vertices. And this is like the log of the number of vertices. So you're keeping track of the log of the number of vertices, log of the length of the path. The length of the path is at most the number of vertices. And this is, so C is actually bad notation on my part. So I'll put alpha, and I'll say this is just some constant. I shouldn't use C here. So alpha is there because this is some, so you can think of this as 2 to the alpha S of n vertices. Okay? And then what Savitch did was he wrote like a recursive procedure for this through a recurrence. So I'm going to give you a logical formulation. Then I'm going to sort of abstract the problem out and tell you the basic problem. Okay, so now, does this make sense so far? Any questions about this? Okay.
So we're trying to create a procedure which computes this reach.
Exactly, which computes this predicate. Yeah.
Okay. I have a thought that, I don't know if this will go directly towards doing that.
Okay, go ahead.
I have the thought that we can't store the entire graph.
Right.
But we can kind of sweep through all of the vertices.
Yes.
By, just having a variable which keeps track of which one you're currently on, or like its encoding and so on. So maybe I have a guess that maybe somehow that might play into it, but I don't know.
So the sweeping, so the problem is that you're essentially trying to solve like a BFS type question without doing a BFS. You're trying to solve reachability without doing BFS. Right? That's the key.
It's like trying to do BFS, except you can only look around your current state.
Right. So when you start thinking of it that way, it becomes really tricky, because you cannot, what if your path loops back to itself? Like, let's say you have a long path and you're following this path and it loops back to itself. I mean, you can't even store the entire path.
Yeah, because it could just be the entire graph itself.
It could be almost it could be exponentially many, it could be 2 to the O of Sn nodes.
Yeah.
So let's actually, so I want to first make sure that everybody understands this, because then I'm going to abstract this problem out into a graph problem that we can think about without worrying about Turing machines. And once we think about that problem, we get the solution for that problem, Savitch's theorem will just be a consequence. Okay, so any questions about this formulation? What we're going to do is we're going to do some recursion on this. We're going to use this procedure recursively. Okay, before I give the abstract formulation, let's talk about the base case. So reach C start, I'm sorry. What about reach C prime 0? What does this procedure mean? When is this true?
Well, that's if the start state is the same as the accepting state, right?
So this is not the start, Nick. These are just two arbitrary states.
Well, its length less than or equal to 2 to the power of 0.
2 to the power of 0.
Oh, right.
The immediate neighbors of the accepting state.
Or in this case, not accepting, but just two arbitrary states.
Oh yeah.
Right? So C and C prime are just arbitrary states. So this is true if and only if C prime is an edge. Right? Which means that the Turing machine M can go to configuration C prime from C. So reach C prime 0 can be decided in O of S of n space. Right, because just given the configurations, you can imagine a procedure would just go and check, is this the next can this configuration follow? Now, regardless of determinism or non-determinism, just has to check one step of the Turing machine. Is this clear? So I want to step back a little bit. And let's understand what's going on. There is a procedure. Okay, so we need to check if there is a path in G from C start to C accept. I'm going to write this as a predicate where I'm going to also keep track of the log of the length of the path. So I'm going to define a procedure, or it's actually a procedure and a predicate both, that given two configurations C and C prime, not necessarily the starting, just C and C prime and I, returns true, or this predicate is true if there exists a path from C to C prime whose length is at most 2 to the I. Otherwise it's false, right? So this is just saying, is there a path from C to C prime of length at most 2 to the I? Right? 2 to the I, not I. And so as we discussed, reach of C star to C accept, with the I being alpha times Sn, where alpha times Sn is a bound on the total space. This is true if and only if X is in the language. So this predicate is what we need to determine. And I'm going to show you how to do it recursively, but let's just look at the base case before we get there. So the base case is given two configurations. To determine if there is a path of length 1, that's easy because you can just look at, this can be done in O of S of n space. just using sort of the transition function of the Turing machine. So let's now talk about a graph problem, an abstract graph problem. So consider a directed graph G equal to V comma E, and we'll just say that V is equal to K. So it has K vertices. And so we can, as before, we can define reach U V of I. Okay? And then what we'll assume is that reach UV0 can be decided in, now this is important, in O of log K space. So I said log K because the total number of vertices is K. And so that's log K, right? You can think of it as K. This is what I said was K. 2 to the O of S of n is K. So S of n is going to be log K. It's going to be log K. So reach.
This space is basically just enough to hold the encoding, or like a label for the vertex.
Exactly. You just need to hold the labels, and maybe you need a little bit of extra scratch space. But it's only a constant factor more. You just hold the two encodings, and if you put the two encodings, you can look up and you can check whether one configuration moves to the next. I mean, at the very least, you can obviously see you can do it in O of S of n time, and so O of S of n space is also all you need. You can use some extra space, but it's only a constant overhead. Okay, so reach. The key is to say the following, that this, thinking of it as a predicate, is the same as saying there exists a vertex W. There exists a vertex W such that reach UW I minus 1 and reach WV I minus 1. So this is the clever part here. What this is saying is, if you can get from U to V in a path of length 2 to the I, there has to be an intermediate vertex. So just to draw a picture here, so here is U and here is V, and if there is some path of length, if this length is less than 2 to the I, look at the midpoint, call that W. And this is of length at most 2 to the I minus 1, and this is of length at most 2 to the I minus 1. So this is if and only if. You can reach from U to V in less than 2 to the I steps if there exists an intermediate vertex W, so that you can get from U to W in less than 2 to the I minus 1, and you can get from W to V in less than 2 to the I minus 1, less than equal to. Does this make sense? And this gives me my recursive procedure now. So I'm going to give the procedure. So I'm sort of abusing notation, and I'm saying the procedure and the predicate are sort of the same thing. So I'm giving you now a procedure for this. I'll say first the base case is if I is equal to 0, then decide reach UV0 in O of log K space. This is sort of by assumption. We assume that we can do this. So this is just checking if this is an edge of the graph. Think of this as like, this is just saying that this is maybe like a lookup or whatever have you. Okay. Otherwise, you do the following. You say for all vertices W, check if reach is true. Or I should actually make it even simpler, right? So you run this procedure, and then you run reach of WVI minus 1, and you say if both are true, then you output true. Otherwise, you just output false. Okay, this is the entire code for reach. So if I is equal to 0, that's the base case, which means it's just an edge. So you're saying, here's U and V, and you're checking if there's an edge. This is just the base case. This can be done in O of log k space. So we agree that this is sort of the setting that we have. Otherwise, you go through all vertices W. So loop over all the vertices. So this is similar to the sweep that was mentioned, that you can loop over all the vertices in O of S of n space, because you can afford the time to do it. You cannot afford the space to write down all the vertices separately, but you can reuse the space. So this is reusing space. So for all vertices W, you run reach U to W with I minus 1. You run reach of W to V in I minus 1. And if both of them are true, output true. And if neither of these vertices have both these properties, if no vertex W are both of them true, you just go ahead and output false. So is it clear why this procedure actually is correct? Is it clear why the procedure is correct?
So the reason why we can, take I minus 1 is because it's essentially like we're dividing the path in half, right?
Exactly.
The path length.
Exactly.
Got it.
So we're dividing the path length in half. And this is now the clever... Okay, so there are lots of clever bits here, but... So what is the recursion depth?
It's going to be log of the number of possible vertices.
It's log of the number of vertices, so it's log k.
See.
Which, going back to this, the recursion depth is going to be S of n. That's the recursion depth. So instead of trying to construct the entire path, so what is remarkable about this procedure is it doesn't output the path, because it keeps rewriting its own space. Okay, so now, but we need to think about it. So, okay, I'm going to write this claim. So, this is a claim that hopefully you can convince yourself of, is that reach UVI outputs true if and only if there is a path of length at most 2 to the I from U to V, and the proof is just by induction. It's just induction on I. Okay, so I'll leave this as an exercise. So that's the proof. Now we need to... Sorry, go ahead.
I have a thought, which
okay.
is I'm kind of imagining how this could be kind of phrased in a sort of like kind of like giving a set or like a candidate like sequence of hops in this sort of sense. So I'm imagining like you could you could first decide that you are going to look for a set of vertices, the set of which, or like a set of vertices no more than log k, and and basically ensure that the first vertex is within within reach 0, and then the next one is within reach 1 of the next one, and so on.
Yes.
And then you could kind of turn that, or after you determine that the last one, or the second to last one, is within the log k minus 1 reach, then you can apply the rest recursively down to the rest of the list.
Exactly. You're going sort of bottom up, but it's convenient to think of it top down. That instead of sort of trying to go from U to V, instead it makes sense to get the midpoint and then recursively get midpoints. And as long as you can get, in every stage, as long as you can get the midpoint within a depth of I, then there's a path of length at most 2 to the I, which is essentially rewording what you just said. But let me do sort of the space complexity analysis formally. So we have to be a little careful about that. What I want to make sure is you're convinced of the claim. And I don't want to write out the proof in gory detail, because that's not the point. I want you to see the idea here. And again, forget Turing machines, forget space complexity. You're given a graph and you have to tell me, can I get from U to V in a path of length at most 2 to the I? And you're trying to come up with a space-efficient procedure to do this, which doesn't actually construct the path. And that's the remarkable part of it. It doesn't construct the path.
Could it? As in, would it be possible for it to, kind of, or not store the whole path at the same time, or not store the entire path at any point in time, but kind of step by step move towards the state that you're trying to get to?
So it can, the question you're asking is, can it sort of implicitly give you the path? And if you think about it, okay, so we will see this, that it's going to build some kind of recursion tree. And if you do some kind of pre-order, if you do an in-order tree traversal, then it will actually give you the path.
That's pretty cool.
Okay, we'll see that shortly. Okay, I'm going to assume that you understand this procedure now. Now the question is, how much space does it take? How much space is required? How much space to implement or to run reach UV of I? Right? This is the question. So I'm going to define, I'll say SP of I. This is sort of the space complexity of reach UV of I. Where, I should say the space complexity of the max over UV of reach of I. Right? So I'm fixing I, but then I'm saying what is the worst case over all possibilities. So this is the space complexity of reach of UV of I, and I'm going to define that as SP of I, and I'm going to write a recurrence for SP of I. And write a recurrence for SP of I. Now remember that there are 2 to the k. So there are k vertices over here. So we'll write this in terms of log k. And remember, just to remind you, k is 2 to the O of S of n. So log k is basically S of n. Right? O of log k, up to O. Log k is S of n, and k is 2 to the O of S of n. Okay, so I'm going to write a recurrence for the space of this procedure. And now let me ask you, what is the recurrence for S of I? So note that S of 0 is O of log k. This is just this part here, right? S of 0 is O of log k. So what is the recurrence? So I'm going to give you a bunch of options and you tell me which one. S of I plus 1 is at most S of I plus O of log k. S of I plus 1 is at most 2 times S of I plus O of log k. Or is S of I plus 1 k times S of I plus O of log k. Think about this carefully. What is the recurrence? So assuming you know, maybe I should have written I should have written I and I minus 1, but it's the same, right? It's the same thing as I plus 1 here and I over here. I'm just going to go over the output false. Okay, there it is. There's everything. What is the recurrence? How much space is used in the I plus first call? Okay, so it's sort of split between A and B. Does someone want to explain why they chose one of these options?
Well, here's what I was thinking.
So what option did you choose?
Oh, I chose A.
Okay.
I was thinking that B kind of seems like it would be the case, or like where you kind of like store the entire path. Or like it feels like that's how it would recurse.
Mm-hmm.
Whereas A, it kind of makes more sense to me because like after you run one of these subproblems,
These,
then you only really need log k space to like store the kind of output of that, and you can reuse your space to compute the next one.
exactly. So actually, the output is just a single bit. So you don't even need, but you're absolutely right. You only need log k space to store the vertex W. So because you have to keep track of which vertex in the loop. So you're going to store the vertex W. You're going to use S of I space to compute this. Once you get the answer, you store the answer. And then you go here and you reuse the space to compute this. Now, if both of these were true, you output true. Otherwise, you clear everything and you start from scratch. So you're only going to use S of I plus O of log k. This is to store W, and this is to solve one of these problems. And I'll write this again. I write this out in some amount of formality. This is the recurrence here. Let me explain why. Let me see if I can keep these sort of side by side. So let's sort of Let's sort of see if we can get this out side by side. So remember, this was the procedure. Okay, so I'm just going to sort of ignore the base case. I'm going to see how do you implement this loop. So first, store W. That's O of log k space. Compute reach u w I minus 1. Okay, this is basically S of I space. Store the answer. And this is, the answer is just a single bit. But you can go ahead and you can store it in O of log k space. Then you compute reach wv I minus 1. Reuse the space. So you don't need this space anymore because you have the vertex w and then you have the answer to reach u w I minus 1. So you just reuse the space and then you store the answer. Again, you can do this in O of log k space. So you check both answers. If true, done. Otherwise, increment w. And you go back. Remember, you're storing w, right? So you increment the w because you can think of it as it's just a string. So you move on to the next one. You can just add one, or you have any ordering on the strings. So you increment w and clear all the other space. Does this explain? Do you see why it's just O of log k plus S of I space? You get to reuse the space. You also, for the loop, think of it, if you have a loop variable, you don't have to store the entire range of the loop variable. You just store that loop variable and keep incrementing it. And so you have log k to store that vertex. And then after that, you're just incrementing it. You reuse the space for these two procedures. So that gives us the recurrence S of I plus 1 is at most S of I plus log k. Thus, and this you can go ahead and do it by induction, is O of I log k. Which means that S of log k is O of log squared k. And the path length is at most k, which is equal to 2 to the log k. I guess I'm doing log base 2 here. Is 2 to the log k. So to determine if there is a path, there is any path, there is a path of any length, from u to v requires, or I should say can be done, in O of log squared k space. O of log squared k space. Is this clear? And this is a deterministic algorithm, right? This is deterministic. So I should say can be done in deterministic. O of log squared k space. Any questions about this?
time complexity. Are we about to talk about that?
It's a good question. So the answer is
definitely exponential.
It's definitely exponential.
Yeah.
And so in some sense, we're not going to talk about it. We don't care. But it's exponential.
Yeah, it's kind of like, or like thinking about this problem feels a little weird in that sense, because like, feels like you just, or like kind of, I would normally kind of think that you could like remember kind of like your steps that you've took, but if you just like choose to remember everything, then you won't have enough space and stuff. And like another thought I kind of have about this problem is that kind of essentially, well, it's not necessarily obvious through the recursion, but it's essentially looking through a lot of candidate solutions, or like a lot of candidate like hops and such. And normally with like P versus NP, we can't just search through every candidate solution, because, you know, that makes it so that the time you take is exponential necessarily. But here it's kind of like, okay, and I kind of have the guess that maybe this is why non-determinism doesn't matter for space complexities, because you can search through these candidate solutions.
Right, so there is a square. So the space has squared, but up to the square it doesn't matter. So another way of thinking about this is if you look at the recursion tree. So maybe this is the question that someone had about the runtime. So it's a good question. It's useful to ask that to understand the recursion tree. So I'm just going to draw out the recursion tree here. So let me first sort of complete the message, and then I will draw out the recursion tree. So what is the message over here? So to determine if there is a path of any length from u to v can be done in log squared k. So now let's go back to our picture here. We have a configuration graph, and we have to determine C start has a path to C except, and this was k. And so we do log squared k of that, right? So for Savitch's theorem, the k is 2 to the alpha s of n, and so O of log squared k is really O of s of n square, right? So that's how much space. So now we're done with the proof, right? We can decide L in non-deterministic space S of n in deterministic O of S of n squared space. And that completes the proof of Savitch's theorem. But the question about the size is a very valid one. So let's talk about that. The running time is very valid. So if you look at let's just say you're looking at reach u v log k, because that's sort of where it starts at the beginning. How many calls is this going to make? So for every vertex, it's going to make 2 calls. So I'm just writing out the runtime. And so this loop runs k times, and there are 2 calls. So what you have is you have multiple calls being made. Like each call over here goes to reach of, maybe some u prime, or I'll call it u1 v1 log k minus 1. How many calls are there? The number of calls that are made here is 2 times k. Right? It's 2 times k. And how many calls are made here? 2 times k. So it's exploring the entire tree. And what is the depth? What is the depth of this tree? Actually, I should have shown this picture before. In hindsight, this is the picture that I should have shown before. What is the depth of the recursion tree? Is log k. So what is the size of the recursion tree? What is the size of the recursion tree? It's basically 2k to the power log k. So that is the running time. It's actually even worse than doing a BFS. A BFS would only run in O of k time. This is running in k to the log k time. But the k to the log k time you would have seen is basically that's like 2 to the O of log squared k. So in some sense, the size of the recursion tree is this, but what is the size of the recursion stack? What is the size of the recursion stack? That's just the length of the path times whatever it stores to see which call did you make. So the recursion stack size is only O of log squared k, and that's the space. So imagine if you're doing a recursive procedure, you don't need to store the entire recursion tree if you only are looking for the answers. Only you're looking for the answers in a particular way, right? In this case, that you're seeing that these two calls have the same answer. So in that case, you only have to store the recursion stack, which is a stack of calls going down. And the size of that recursion stack, that's just O of log squared k. So that's sort of the idea why you get log squared k space, even though the runtime is exponential in the space.
Okay, so in a way, we're trading in like a lot of time for a lot of space.
For less space.
For less space, yeah.
Yeah, but we're basically trading off, right? So the algorithm is inefficient in terms of running time, but is space efficient.
It's kind of weird to think about space efficiency after, we've been thinking about time efficiency for so long.
Mm-hmm. It does require a different way of thinking. And that's maybe one of the reasons why the things that we're stuck on for time tend to behave differently for space. It does require a different way of thinking.
Yeah.
But sort of remember, putting it all together, what we get out of Savitch's theorem is that PSPACE is equal to NPSPACE. PSPACE is NPSPACE. So non-determinism, does not give more power for PSPACE. I mean, it is quadratic. There is a quadratic. It is sort of quadratically more powerful, but it's just a polynomial. This is one of those proofs that you'll have to go back and look and make sure that you understand. It's not, but the key, as I said, is to really think about this abstract problem. Is to think about the abstract problem of I have a directed graph with k vertices. I want to determine if there is a path from one vertex to another. And the way I break it up is to, in some sense, try to find the midpoint recursively. And that's where, because I'm trying to find the midpoint recursively, I'm really dealing with the log of the length of the path. So the log is going down by 1 at each step. The recursion depth ends up being log k, which is the log of the maximum path length. And because the out degree of the recursion tree is basically 2 times k, I just need to store which of these. I mean, if I'm trying to sort of think of it as you're kind of taking all paths down the recursion tree, you don't need to keep track of the entire tree. So think of it as backtracking. And when you're doing backtracking, you don't keep track of everything that you've done so far. You just sort of keep track of where you are. Right? That's how a backtracking algorithm works. And so the backtracking only requires the size of the recursion stack, which is O of log square k, which is the size. Which is the final space complexity that we get, which is that k was 2 to the Sn, and so log square k, as we said, is Sn squared. And so that proves that P space is NP space.